everyone. In this video, we will discuss how to select frames and designs for high-rise buildings. Finally, we get to this point when we need to understand the role of structural frames in resisting lateral force caused by the wind and seismic actions. And we have completed studying the seismic actions and wind actions, how they affects the building behavior, and especially we studied the R factor when we design frames. And these frames also should belong to one of those categories that we learned in previous class, whether this is a moment frames of intermediate or special moment or ordinary, and we should select a appropriate R values. So we have to always think that our design, our selection of frames must be based on the table that we talked about. Okay, we're gonna start with the short review. So what kind of frame did we learn in previous lecture? We learned that there is a bearing wall structure, and there is a building frame structure, and there is a moment frame structure. And for moment frame structure, we have three types of frames: ordinary moment frame, 보통, 골조, intermediate moment frame, 중간, 골조, special moment frame, 특수, 골조. And we had to select the R factor, seismic modification factor, depending on our selection among these three types of frames. So, and here, especially we have to notice that this building frame system, we should have a pin simply supported frames that is attached to show walls. Okay, this is important for building frame structure. The most of the buildings that we have in Korea called 주상복합 is using this frame. Okay, and if you go in dual system, whereas in dual system we have a moment frame instead of a pin that simply supported frame here. So the moment frame will participate in resisting lateral load, whereas the frame in here in building frame system do not participate. The frames simply supported frames do not participate in resisting lateral force of course. And here dual frame and the building frame, both frames, the frame looks same, but their role in terms of contributing to lateral load resisting system is quite different. In this case, the moment frame should be able to resist 25% of seismic load, shear forces caused by the earthquake, and this is very important. And the 75 is to be resisted by the shear walls. This is for protecting shear walls. If shear wall has to resist 100% seismic load, then it may not be very good. So we have to distribute the contributions of the frames into two frames, shear walls and moment frames. And also we have a reinforced concrete frame. This is, if this is a steel frame, we can still have a moment frame made by concrete, but it is same. We should be able to rely on RC frame for 25% of resistance against the earthquake loadings. Okay, So I think we have studied these 5 structural frames already, right? Don't forget it. Bearing wall system, building frame system, moment frame system, and dual system. As we have 2 types of dual systems, shear walls plus steel frame plus or RC frames. Okay, but these frames are pretty effective to resist the lateral force. For example, you could still resist very high-rise buildings using dual system. For example, the apartments that we have in Korea is rises about 40 stories, something that we have a dual systems, shear walls and moment frames. Sometimes we only have a shear walls. So the shear wall structure or dual frame structure still can provide very effective structural system for high-rise building up to 40-story building or a little less than 40-story buildings. And this is what we have in Korea. But if you are planning the buildings higher than 40 to 50, even 100, over 100, these structural systems, it's not going to be enough. We need some other structural system more effective than those frames we talk about here. And today, we will take a look at some of them. And in coming lectures, I'll be talking about the structural frames that can be used to resist the lateral force for about 40 to maybe 50, 60 to maybe 200, even more, even higher. And what kind of frame systems are available for doing that? Okay, so one of them that we're going to learn today is Outrigger system. Outrigger system. Okay, first of all, what is our legal system? Our legal systems are nothing more than jige. We saw it from our fathers and grandfathers. And also we have one very good example that we use Outrigger in our daily lives. If you hear, this is a Outrigger car, and this is a very good example of Outrigger trucks, which lifted heavy loads all the way up to the high-rise floors. And this overturning is seriously large when you do it, because this is very dangerous. The car can overturn in this way, and you have to put and lift heavy loads to high-rise buildings. And there we have established and installed a outrigger, something like this. And this outrigger will provide you bigger overturning moment capacity, because your moment arm from here to here makes your overturning capacity higher, because the overturning capacity is calculated by P times L, so that your moment capacity is increased significantly. Otherwise, your moment arm is from here to here. The width of your troughs, which is not sufficient to support loadings when you lift it heavier load. But this is one of very good applications and examples that we use outrigger in our daily lives. And you see these outriggers many times, I bet. Okay, this is outrigger. And engineers invented the way that they use this outrigger in their buildings to resist high-rise building, which is very brilliant idea. And we'll study that today. And I'm sure that you have to use one of those outrigger system in performing your projects. Otherwise, it's going to be difficult or near to impossible when you design buildings which is over than 100-story buildings. And the most high-rise buildings globally must have had these Outrigger systems in it. And that's what we can find out from the Lotte Hotel Tower, which is 123 stories. And there is a couple of outriggers inside of the building to provide larger overturning moments. Okay, this is a schematic view of outrigger structures. And this is outrigger. Looks like jige, isn't it? This is outrigger right there. So without outrigger, what's the overturning moment capacity? The arm for overturning moment capacity from here to here, which is very short. And we're not sure about using that short moment arms to resist such a big seismic load here. This is very small. So the engineers invented a way to increase the moment arm to increase the overturning moments. How? By installing a big arms like a jige. Big arms here, which is called outrigger. Okay. And what happens if you have outrigger over there? Your moment arm increases from here to here, so that your moment resisting capacity increases significantly. And this is very good idea and very economical way to increase and enhance your seismic resisting capacity of the high-rise buildings. And we may have one outrigger or two outriggers and three outriggers, as you see in these illustrations. Okay. And what happens here, if you don't have anything, just building looks like just cantilever, as you see over there. But with outriggers, the building is still looks as cantilever, right here. But what's different thing is that your overturning moment changes. Without outrigger here, your overturning moment is the moment that you learned from your structural analysis class or static class, whichever. If you put outrigger frames over there, your overturning moment decreases like this. So it can be compared with the overturning moment without outrigger. So your overturning moment decreases so that everything decreases. Diffraction decreases, your stress decreases, which is good news for engineers. Let's take a look at briefly why your moment demand decreases. The outriggers are installed here, from here to here, and this is the existing shear walls, if you will. And due to the inserted outrigger, your moment of inertia with respect to this axis is calculated, as you see right here, and dHq over 12 is your moment of inertia of the existing shear walls, whereas your moment of inertia for these columns, which belongs to outrigger, is calculated by the moment of inertia of the column itself and the moment of the inertia with respect to the centroid of the building. Okay, now you have to study your previous classes how to calculate, but this is very straightforward, easy. So this A, B square, and this is a square column, then A Q over 12, and the area of your column should be multiplied by the square of the distance from your centroid of your column to the centroid of all frame systems, right there, which is indicated by L1. So this is L1 square, right? But this is big number because you are talking meter square here. But this is very small number. Is the A is less than meter, and you make a cube of it, becomes very small. You can ignore this value, and this term only survives in the calculations, right? And we have 2 here, 1 and 2 and 2 here, right? And this is another one here, so you can do the same thing here, and L1, and this is L2 here, right? So you can do for all columns that belongs to our legal system, and you go and find that your moment of inertia increases, right? So the structural analysis course tells you that the diffractions on the top of the cantilever and the top of the buildings is depending on your M over EI diagrams. Can you recall? Can you remember? Okay, then you just simply go back and spend like a few minutes. So these M over EI diagrams will really have to be calculated to calculate the fraction on the top of cantilever, on top of buildings right there. So consequently, E increases a lot here due to the additional columns that you add with Outrigger. So when you increase your I in denominator, will decrease entire values here, so that your loading decreases, and your loading discontinuity is found at level where you have a Outrigger, of course, right? So you may calculate manually by hand for your projects, because you can idealize your wall by B and D. You can idealize your columns that is inside of the Outrigger system by A and whatever and B, and if that's not a square columns, and that's easy. So after you idealize, you can use just very simple formula. Okay, add them up. How many depends on how many columns you have, and now we easily calculate M over EI diagrams. So now do you understand why we have a benefit by installing Outrigger systems in the buildings? Clear? Very interesting, isn't it? Is that fun? So this is really fun when you go out and design in company in the future. If you want to have very nice practice, like real projects, then it'll help your future career very much. Trust me. Okay, so when you have a Outrigger, then you can automatically install a belt truss or belt girder. You can call it anyway, belt girder, belt truss. So that belt truss is gonna aid your Outrigger, so that your Outrigger floor can have a effective stiffness that contributes to resist seismic load. You see, the Outrigger is installed only one story, like that. This is one story. But some cases, you may put Outrigger in 2 stories, but it is customary for you to put the Outrigger in 1 story separately, so that in that way you can maximize the use of Outrigger and resisting lateral loads, wind load and seismic load, whatever. So here you put belt truss. Okay, this is belt truss. You install a belt structure around where you have a outrigger so that it adds stiffness on the top of your outrigger. Okay, and this is belt truss. So these belt trusses are installed with the outrigger. Okay, you don't have to have belt truss. Sometimes belt truss does not provide you the stiffness as much as you expected, but it is customary for you to put belt trusses with outrigger. And if you put belt truss on the top of floor, it is called a cap truss. The one you see here is cap truss, example of cap truss. So that you may have a cap truss and somewhere belt truss where you have a outriggers. It is very good, but usually the cap truss may not accompany your outrigger structures because you don't put usually outrigger structures on the top of the buildings. So that belt trusses are installed independently of the outrigger frames. So we can put core walls here if you want to use a concrete structure, and you can use a truss if you want to use a steel structures. As you see over there, it doesn't matter. And you have a belt truss around the outrigger frames, and outrigger frames are three in these illustrations and here. And also you may have a cap truss on the top of the buildings, add additional stiffness on the buildings, and you have a columns, peripheral columns to support the outrigger systems. And this is pretty simple structural systems, but it is very effective. You can do and check and compare the stiffness and the lateral resisting capacities with outrigger and without outrigger in your projects, and you will see how important for you to have a outrigger system and designing high-rise buildings. See here. So with high-rise buildings having a outriggers, you want to limit your diffractions, deformations based on this formula. You can have a 400 to 600 depending on engineers' decisions, and I'd rather use 400 for about 60, 70 story, and you probably want to increase this number to 60 when you have higher buildings to make sure that the serviceability, to limit the vibrations. This does not really relate to the building structural safety, but it relates to the serviceability. The building vibration can cause the unpleasant conditions for the tenant. And also, if you have excessive diffractions on the top of the buildings, then it may cause a secondary moment, as I explained in previous lectures. Right? So the secondary moment, M equal SP delta. So this P delta is a structural issue. It may be checked. It has to be checked. So that otherwise the secondary moment causes any problems, then this is simply matter of a serviceability issues. Okay, you have to check both of them. Okay, and also this is also explained earlier, and you're checking the acceleration level, and it also depends on engineers, 10 to 15 gals, and 1 gal is 1/1000 gravities. Okay? 10 gal means 10/1000 gravities. This G represents gravities. Okay, this has been explained, but we'll take a look at it one more time briefly. And okay, if your wind is blowing from these directions, it's easy to recognize that this is a tension phase all the columns and structural elements on windward side. We call this is windward side, the side that receives the wind directly. That side is subjected to tension. All columns are under tension influence. Whereas you have a compression forces for leeward side. The leeward side means the other side of the windward side. We call it windward and leeward. And this is what we call it wind engineering. So the column with the leeward side is under compression. So it's tension and compression. And this tension and compression actions will change if you change the loading directions. That's obvious, isn't it? This is how you Outrigger is cooperated with your structural system which exists in the structure. And of course, if your overturning moment by wind going this way, and then you have to provide a resisting overturning moment that way, so that you can have a resisting moment which is increased when you increase the moment arm of your structure system that we talked about. This is amazing concept with very economical, affordable cost. And here you're gonna take this and check in your project as well. And this is diffractions without Outrigger system. This is a diffraction with Outrigger system. Okay, without Outrigger system, with Outrigger system. As you see over there, the diffraction decreases significantly. Is over there because of the Outrigger system, which then increases moment of inertia that we talked about a few minutes ago. And this is what M over EI diagrams. Right? So diffraction is function of M over EI diagrams. So you want to go back to structural analysis course and take a look at the diffraction of the system, the moment area method. This is nothing more than a moment area method. Moment area method. So you go in and calculate what is moment area method for calculating the cantilever diffractions. It is very straightforward, isn't it? So if you have a loading over there, first of all you have to calculate moment divided by EI diagrams. We call that M over EI diagrams. We calculate M over EI diagrams, and then we calculate the area of M over EI diagrams. Then also we calculate the centroidal distances from the centroid of M over EI diagrams and the point of loadings, which is in this case L. Okay, if this is a triangle, then we know that this is 1/3 h, this is 2/3 h, isn't it? But if we have some curve functions, second polynomial, third polynomial, then you may have to use a little bit of mathematics to calculate the centroid of the M over EI diagrams, but you don't have to, because you can use a numerical way, this way. So each little element, and we know where the centroid of each little strip element, here and here and here, right? Can I redraw here? Okay, no problem. So if you have a very complex curve and you need to calculate centroid of each, so we may have 5, 6 segments first of all, and you know that you assume that this is rectangular this way. So this is cancelled with this one, and this, this cancel this. Right? This is a approximations, right? Approximations. If you have so many elements, then this approximation will yield a real solutions, right? Exact solutions. We know that the center of each rectangle is the center of the centroid, and you multiply this area and this distance plus this area times this distance plus this area and this distance times plus. So on and so forth. And that way you don't have to solve for mathematics. You can do this numerically, something like this, right? But you can make a Excel, a little software code and calculate. So this is how you calculate your diffraction at the tip of the high-rise buildings and compare the one with Outrigger and without Outrigger. Okay? And this is a preliminary design checks before you going into the Midas. So Midas takes sometimes, so that you don't want to wait until Midas is completed. And also you want to put the good size as good as possible, into the Midas. Then you want to just carry out some hand calculations, something like this, and decide what input that you want to use in initial Midas inputs. And they can save your trial and error efforts, thus saving your times, and you can finish your projects as soon as possible. This is very nice illustration that giving you idea where the Outrigger must be placed. I mean installed, right? So without any Outrigger, okay. First of all, what is this structural systems looking? What do you think this structural system must belong? To me, this is a dual structural frames. So-called dual frames. You have a core truss here. You have a frames out there, so that you have a core and frames. To me, if this frames supports a lateral force, then we call that, yes, dual system. If this frames out there do not support lateral system because the frame is built based on simply supported conditions, then we call that building frame. Either building frame or dual frames. I have no idea, but such high-rise buildings, it is probably built with a dual system. That's what I guess. And you have a Outrigger's locations varies from here all the way to here, and you see the diffractions. Diffractions decreases as your Outrigger is located towards top locations. Maybe your smallest diffractions when you have the Outrigger near the top of the building, whereas you have a significantly big diffractions when you install your Outrigger in the bottom. Okay, then this must be giving you an idea where your Outrigger must be placed. Okay, and here another example when you have two Outriggers. Right? So when you have two Outriggers and one Outrigger is fixed somewhere here, and then you change your Outrigger floors and see how your diffraction decreases and diffraction evolves to better design. Okay, and you can do same analysis with 3 outriggers and 4 outriggers. It really doesn't matter, isn't it? Okay, does this illustration gives you better idea what outrigger is doing for you to resist the lateral force? I think so. Here we have a outrigger and with the belt truss, 2 outriggers in the mid height and 1 towards top height. Okay, and we have a outriggers right here, and right here, and you see how the immovable EI diagrams changes, thus reducing your diffractions, and this is very good. And also this is very simple to simulate using MIDAS. And I'm going to see one of the computer outputs illustrations after you put outriggers at the end of lecture today.